Oh, no. All right, there's that one.
Right, Duncan, on 1 minute. Maybe you should speak out loud the title.
There we go.
of your talk.
1 million IO ops.
Into the microphone.
1 million IO ops. Right, so SSDs are fast. We know that. So here's the one on my laptop. This is the FIO benchmarking tool, standard Linux tool. And with QDepth 1, which means serial, I get 12,000 and a bit operations per second. Right, okay, that's faster than a hard disk, but it's not great. Next, that's what you get in parallel, right? There's a massive difference between the serial performance of your SSDs and your parallel performance. That's QDepth 32, and there's a factor of 20 parallel speed up from going parallel with your I/O. Now, in Haskell, at the moment, we can only really do that, which is disappointing, right? Because if you're using mmap, if you're using just ordinary file reads or writes, you're not getting any genuine parallelism when you're doing I/O. And that is sad. We can write really nice, high-performance concurrent network servers so long as they don't use the disk. That's disappointing. I want to be able to write ones that do use the disk. Okay. Now, okay, so this is, I'm presenting a partial solution to you, and then advertising, we can do better even so. So block IO-uring is a library that we've written, which is a binding, unsurprisingly, to uring, IO-uring, which is a Linux API, a Linux kernel API to do high-performance asynchronous parallel IO. And we're getting comparable, in fact, ever so slightly higher results on a single core than FIO. So now we can get our hundreds of thousands of IO operations per second with a Haskell library, and it's actually quite a nice API. Just very briefly, here we are. Oops, I need to scroll up a little bit. Can you see that? Is that too small? Zoom in, zoom in. Right, submit IO. Don't worry about the context. You give it a vector of IO operations, and it gives you back a vector of results. So you submit an entire batch of things, and it gives you a batch of results. And the IO operations themselves can be reads and writes on any file you like. So you can have a batch of, it doesn't have to be the same file, it can be on a bunch of different files. And in to or from mutable byte arrays, which must obviously be pinned. And you can execute multiple of these things concurrently. So not only does it not block other Haskell threads while submit IO is going on, but you can call submit IO from multiple Haskell threads as well. And the benchmark that you saw just a second ago is actually using 4 Haskell threads on a single capability, which is probably why it gets ever so slightly higher result than FIO itself, which is otherwise pretty much unthinkable. But wait, we can do more. I said 1 million. That is not 1 million. It turns out, with modern SSDs, you need to use multiple cores to get the full I/O throughput of your high-performance SSDs. Turns out that my SSD on my laptop, which is not anything particularly fancy, can do nearly 1.5 million I/O operations per second if you use it on all 8 cores. And with block IO-uring, we can get pretty close to what FIO can do. So I think that is a big win. We are actually using this in production in a library for doing on-disk key value store. And we can get hundreds of thousands of lookups per second. But the library, we're publishing the library soon. It already exists, so that people can use it for whatever they like. Thank you very much.
Can this be a practical way to if I just write normal IO operation, like a fork a bunch of threads?
Yeah, okay, so what I really want to do is change the RTS IO manager to use IO-uring. That's what I really want to do. But in the meantime, here's a library. Yeah, I've been working on that for 3 years. It's on and off, mostly off.
I'm not super familiar with the underlying technology. Does it mean it only works on Linux?
This particular one, the block IO interface is supposed to be portable, but the uring implementation is obviously uring specific. You can imagine, unfortunately, Mac and Windows have different APIs for achieving high performance with SSDs, sadly. But the APIs exist on each platform. They're just all different from each other, unfortunately. you have time for one more at the back?
From the interface, it looks like you always have to wait for the slowest result.
Yeah, this is a last to finish synchronization of that batch. But you can submit multiple batches independently, concurrently.
Okay.
Yeah. So that's kind of for convenience. So it's still blocking in a sense, but you can submit multiple concurrently, and it doesn't block other Haskell threads.
Okay, I wasn't
Yeah.
sure whether block meant block device or block in, sorry.
Yeah, so that block is block device. Oh, there's one more little detail, actually, which is that this is also using, this is a feature we added into the Unix package, is that you can now set file caching to turn caching off, meaning that you're using direct I/O mode. So to get really high performance on SSDs, you have to be using direct I/O, which means 4K aligned offsets and buffers and all the rest of it. Otherwise, and the FIO was using direct I/O as well. So those benchmark results were with direct I/O, and so we can do that now with Haskell too. That's in the latest version of the Unix package.
Thanks, Duncan. Next up, we have Yaro on adventures in Typeclass.
Typeclass resolution.
Typeclass resolution. Okay. The Excel was truncating part of the title.
Yes. So I have a few slides about typeclass resolution. What are typeclasses? This was originally written for a different audience, but I assume you all know. One important thing I want to stress is they allow us to avoid writing certain repetitive parts of our programs, and that's perhaps a bit of a mind shift from normal Haskell usage. But typeclasses have some limitations. So I found online some posts, for example, this one by Martin Escardo about teaching typeclasses to students. And he's saying, having to define a functor instance and an applicative instance just to get to my monad is a lot of work. I just want to have my students implement and just want to only teach this one monad class and then have it derive the functor and applicative instances from that monad type class. Unfortunately, so the way he's doing this is by instances, or he suggests doing this, is by instances which say this new super monad type implies functor and implies applicative, and you can easily write these instances. Unfortunately, there's the instance head restriction where the instance resolution mechanism only looks at the head, which is this applicative part, when it's resolving instances. So it commits to this instance before it looks at anything else. And I mean, this instance says any type variable is a monad. So this instance will actually conflict with all other applicative instances for all other things which perhaps are not monads, are not also these, don't have instances for this supermonad. Similarly, there was another question on Stack Overflow where someone wanted to define heterogeneous equality. And like, for example, if you want to compare ints and booleans for equality, you could say that 1 is true and 0 is false, and all other things are false, or all other things are not equal. And then you want to write an instance like this, where you say that if we have an equality between A and B, we also, of course, have an equality between B and A. And I mean, you can try very hard using undecidable instances and overlappable pragmas, but this will always, so that will work if you have an instance like this and you try to flip the arguments, but that won't work if there is not an instance, and then it will just, then it's just undecidable whether there is an instance because it will go back and forth all the time. And my own use case is a kind of parametric higher order abstract syntax wrapper around the Brown indexed lambda calculus representation. And here I'm using scopes, which are these S's, and I have the type class which says the scopes can be included in each other, or you can have subscopes essentially. And well, for this class, if you have an index into the scope S, and it's a subscope of S prime, then you can translate it into an index of S prime. And using this interface, I wanted to be able to write, for example, this lambda calculus expression, which introduces a new scope at every lambda. So this x belongs to scope S1, and then it introduces S2 and S3. And then when you use it, you need to know that S1 is a subscope of S3. And to be able to resolve things like this, I want to write instances like a scope is, of course, included in itself, and you have this transitivity. And that should give GHC enough knowledge to be able to resolve that this S1 is actually a subscope of S3 in this point. Unfortunately, well, here we have the exact same problem. The head is completely unconstrained, so GHC's normal inference mechanism doesn't work. So I have a little demo of a GHC plugin that I built to... this is too big. To do the instance resolution myself. Okay. So I've called this a transitive constraint plugin because at the time I was only interested in transitivity. I found out so the way I've set this up is I have this sub module which includes this sub-scoping constraint. Here it's slightly different than on the slide, but let's ignore that for now. And then I have this sub-instances module where it has these transitive instances. And the trick is, I added a warning here, do not import this module. You should never use this module. This should only be loaded by my plugin. And that's how, so the plugin, when it initializes, it looks for this sub-module to get the class, and then it looks for the sub-instances module, and then it loads the interface of this sub-instances module, and it looks up the reflexivity and transitivity instances just based on position in that module. I wish there was a better way to do it, but I don't think there actually is, because also when I was reading the GHC documentation, the way you resolve orphan instances is also kind of hacky, I feel like, but maybe I should discuss that with some people present here. So what this does is let you do. So here's an example program that I wrote without a plugin. And the thing I want you to notice is I have to write a lot of these E extension functions, and whenever I use a variable, I need to apply these functions to map it back into the right scope. So these E functions translate the variable from one scope to a superscope. And that's a lot of overhead that I don't want to type. So now, with my plugin, I'm able to write, just directly use these variables. So I still have this weird colon greater than, which is just for heterogeneous lists. But you can now essentially use normal Haskell variable binding, and this produces the Brown index representation, which is the last thing I want to show. If I run this, it generates a very unreadable De Bruijn index representation of the program. So, thank you.
Felix Klein, a Haskell plugin for typeclass proofs.
Yeah, so hi, I'm Felix. I'm from QBlogic, and we are basically the people behind the Clash compiler. For those of you who don't know, that's the compiler which allows you to translate Haskell directly to hardware. And as it turns out, if you do that, it's quite useful to use type-not indexed types, and then you may run into some problems, and this is what this talk is about. So actually, to get to the problem, let's say you want to play a little bit around with type naturals, and this gives you a constraint operation. So here I just pass some S-nuts in. The important bit is that we want to have this constraint on the naturals so that n is smaller than m. And it's not important what the constraint operation does, but now at some point you want to use that operation, and you may have a slightly different constraint. And then you get the non-satisfying error that you cannot satisfy that constraint. But if you look closely, then you see, okay, I actually know that n plus 1 is smaller than m, should imply that I also know that n is smaller than m. But this evidence is not there yet, and GHC has no knowledge about this evidence, because this is a slightly simple argument, but in terms of what you can give as an argument, it can get quite complex. So that's the problem. There already exist solutions to that, so there are various plugins that can help you with that. Like you can normalize the terms and try to figure out it by that. There's a SAT solver plugin to do that. And they work really well, so let's say 90 to 95% of your problems go away with that plugins because they detect how to solve it for you. But as I said, it's only 95%, so there are sometimes some missing expressions that won't be solved. And if you run into that case, you basically are stuck at the moment. So the only solution alternative that you had is you can introduce a dictionary and then use unsafe cores on that dictionary. But that's not really what you want, because we actually had that in production code that one of those unsafe courses was wrong. And luckily the reviewer detected it. But yeah, you really like this to be like real evidence to do so. And the idea here is to alternatively to just extend these kind of automatic solutions is to use a proof assistant that gives you basically full control about what you like to prove, but in the context of this type evidence. Okay, so how does this work? So we basically make use of the class system for Haskell here, because it turns out to be quite useful. So we need undecidable instances and superclasses, but that's not a big deal. So this is now to read a little bit. So you can define a class which basically gives you a name for the thing you like to prove. I call it lemma here. And then the proof goal basically is a superclass of that newly defined class. And then you can define an universal instance who has another superclass, which basically gives you the precondition to prove that. And you can introduce that with GHC without any problems. As long as you don't use the instance, it will never be checked, so it won't complain. But that's basically the way to make GHC aware of it. And then what we additionally have, and this is where the plugin comes into play, is that we can introduce a so-called proof comment that needs to use the same name. So this is basically the preamble to introduce this, and then you can give it a solver. Currently we're supporting Coq and Acta, but we have a backend to add more to that. And from that start, what you can do is you can just run it with the plugin enabled, and then it will create you a proof file with that within a designated path that you then can fill in with the actual proof. And the idea is, this is how it looks like for that particular case, is that you can use whatever IDE environment you like to use with the proof assistant, because we don't like to reinvent the wheel at that case. So this is what you get, and then you basically can use your IDE, and this is a particular proof, probably not the nicest one to prove that statement in Coq. And the idea is then once you have that developed, you can copy it back into the Haskell comment, so you have all your evidence in one place of source. So this will look like this then. And what the plugin does for you now in the default case is that it automatically runs Coq and checks this proof to create the evidence. You can disable it because maybe you want to share the package on Hackage later on, and not everybody has Coq in their parse. But that's the basic idea. So this is how to introduce the evidence. And the final bit is to also make it usable within your code and shareable. And there the class system comes really useful. So the final thing we have is a nice class that is called QED. So first of all, we have our own dictionary type, just because we don't want to depend on anything existing for that. And then we have the QED class, which basically says whatever you can prove, you can make it proven as a constraint. And then you have two methods that allow you to basically use that evidence. So you can either strip the constraint requirement because you have it proven, or you can use the dictionary as you used before. And the naming you will see in a second comes useful in reading the syntax. So the final thing you need to do, and this is actually where without the plugin GHC would complain, because this needs now to be checked, is that you can QED your lemma. And then you have various methods to apply that. So either using the dictionary, which may come useful if you want to apply these rewritings in a particular order, or you can use the the continuation style. Or what we also have, but this is a limited feature, is we have the so-called autoproof. So if a wanted pops up in the plugin and we have a QED instance for that particular wanted in scope, and all the preconditions are in the actual givens, then if this is an exact match, and this is the only condition where it applies, because otherwise we run into a lot of trouble, then it automatically can insert it. And yeah, that's basically what I wanted to show. So what one would do next? So one big issue is custom type family support. So it would be nice if we have type families mostly talking about natural computations to also automatically translate them into the prover. This is a little bit tricky because most provers require total functions. And it may be that your function is total, your type family, but the argument for that is non-trivial. So you need to also ship a proof for the totality for the proof assistance. So we haven't found a nice solution for that yet. And yeah, then more proof assistance would be nice. Also, we are currently only developed for 9.10. We like to extend that to newer GSU versions. And there's a lot of code base that is similar to the already existing plugins. So it might be nice to use that. Finally, as a short add, so this is part of a bigger project we are currently running, which is called Clash Formal. The idea is that we are able to verify hardware that is generated purely in the Haskell ecosystem, where we also look at other approaches. If you're interested in that, I'm around during SuriHack. Just note me. Thanks. Yeah.
We've been talking yesterday, I guess, and maybe also today, about how much everybody hates writing plugins. Could this be done as with template Haskell instead? Like, you can imagine doing it at the start of like inline C or something, and you'd have inline cop, and that would produce some typeclass declarations, and then you maybe don't need the plugin, which might make it life easier.
You mean that you call? So the question is whether we could use template Haskell to inline the coq code at that point. So I guess the idea is to call the coq in the template Haskell definition at that point.
So, but like you do there, you have the coq in the comment, you put the coq inside your inline coq template Haskell thing, and it would produce the typeclass.
But the problem is that you need to still give it to GHC internals, because that error won't go away with template Haskell at that point. So the initial problem that you get the cannot satisfy constraint
you
is.
Still need the QED stuff.
Okay.
You produce exactly this.
But that requires a plugin. I mean, you need to provide the evidence at the plugin level. I don't know of any direct mechanism with GHC to do that. Or an unsafe course, but yeah.
So is it basically that the plugin can create a trust number that can axiom evidence, and you can't do that from that?
For that particular proof that you like to request, yes. I mean, still, if you disable proof checking, then it just creates the evidence without checking the idea. But the idea is that you have a link to the actual proof that gives you evidence that your statement is correct.
No, but I mean, like, is that the point that from template Haskell you have no way of just making a trust me pro evidence? Is that the reason that it couldn't be done?
At least I'm not aware of how to directly integrate that with the type checker. Yeah, other than unsafe course. Yeah.
But that seems like an okay trade-off, right? I mean, it's the instance is essentially the evidence you're generating is essentially an unsafe course, anyways, isn't it?
Yeah, it doesn't seem any different. You're just doing it in type checker currently rather than
Yeah.
fully unsafe course.
Okay, let's continue the discussion and break.
Yeah.
Thanks, Felix. Hackage with Glean.
Okay, I've only got one slide. So those who weren't here yesterday, at Meta we've been working on the system called Glean, which is a code indexing system. We use it for indexing all the code at Meta and supporting various developer tools like code browsers and code search tools and things like that. So I thought it might be fun to try and index all of Hackage by generating all the HIE files using GHC and then ingesting the contents of these things in some way into Glean where it puts them in a database, and then we can make various queries, and let's see what we can do with that. Okay. So I'm going to fire up the Glean shell. So this is the Glean shell. You can interrogate DBs and make queries and things like that.
Mic hold while you're typing.
Thank you. All right, so we can have a look at which DBs we've got available, and one of those is the Stackage DB. So let's have a look at Stackage, and we can have a look at some stats to see how big this DB is. It's about 1 gigabyte of stuff, and it's divided into various what we call predicates. So these predicates are like data types. They're defined in this schema. So the schema is over here. And let's look for, say, name. Okay, so we've got a predicate called name. It's very similar to the GHC name data type. It has a similar sort of structure. It's got an OC name and it's got a module and so on. So we can write some queries and we can do things like, so we want to find a name. Well, actually, let's just have a look. We can find all of the names, and it gives us the first 100 results. And they're in some random order. So let's find a particular name or some names. So we want to find names that have an OC that looks like the name inside the OC should be something that begins with deprecated. Let's find deprecated things. And there are 56 names throughout Hackage that begin with deprecated. Okay, and we can... so let's find constructors instead of just random names. And constructors have to begin with an uppercase letter. So deprecated constructors, oops, what have I done? One closing brace, thank you. Yeah, so there are 7 of those. So we have a thing called, let's see. So we can go from references to their declarations. We can also go in the opposite direction, so from declarations to all of the references of a name throughout the whole of Hackage. So HS name refs. Let's find. Yeah. So the target, we'll find all of the references to all of the things that we were finding previously, all these deprecated constructors. What have I done there?
It's missing. It looks like it's missing a constructor, like after target, maybe.
Target equals. Oh, it's just. Yeah, it should be just that. There we go. Okay. So we can see. Let's pick one by random. So deprecated text. Here are the references or the uses of this thing in this particular file. So, for example, so those are some of the sort of queries that we can do. There's also a higher level interface to all this stuff. So we've got a service called Glass that sort of sits on top of Glean. It makes queries and it has a much simpler API. So it has an API that's defined in terms of just symbols and files and things like that. Stuff that you might want to do in a code browser or an IDE. So, for example, we can find all of the symbols inside a file that I care about, which is control concurrent async.hs. So this gives you a list of all the symbols, and this also decoded all the types as far as possible for many of these symbols. So these things are all what we call a symbol ID. It's a unique string that identifies a particular symbol uniquely throughout the whole code base. And so we can also find references for one of these things. So let's find references for the function map concurrently from the async library. So that finds all of the uses of this thing throughout all of the packages in Stackage. Yeah, that's pretty much all I want to say. Thank you.
We do have time for a couple of questions.
Yeah, all the types are indexed, but not in a way that's easy to search at the moment. Yes, in principle, but not just yet. Yeah.
Have you done any work on verifying the indexes? And by verifying, I mean the indexer does capture all the references in the code.
I haven't done any verification. No, I mean,
in
so
general at Facebook, was that like is because you couldn't miss all the dislocated.
Yes. Yeah. So one thing we used to do was compare Glean's result with Clang's results for C++. And then we would find all the places where we were missing references in Glean and vice versa. Actually, we got to the point where Glean was slightly better in some cases than Clang. If you have a source of truth, then you can do that sort of thing. You can also say, well, we expect to have a reference on every single alphanumeric identifier within this source file, except for keywords, perhaps. Duncan?
Can you have multiple versions of the same package that loaded in at the same time?
Yeah, absolutely. Yeah. The source files, in this case, the source files are all, versioned, so you can certainly do that.
But when you were showing like the identifier of something from the async package, that didn't have any version number in it.
So the name, sorry, say that again?
Like you showed us that you have like this identifier of entities. I can't remember.
Oh, the symbol IDs, yes.
That one didn't seem to have a version.
Yeah, I stripped out the version numbers from those. I suppose if you're going to have multi-versions, then you should change the symbol IDs to have versions in too. Yeah. Duncan?
How big is the database?
A gigabyte.
Gigabyte, in gigabytes.
Yeah. Is it 1 gigabyte?
One.
And currently it has all of the declarations, all the references, cross-references in both directions, and the types as well.
Oh, but it doesn't have like the right-hand sides.
It doesn't have the full ASTs of the bodies of the functions, no. No.
How long does it take to load all the AHA files?
10 minutes.
That's impressive.
Is the code for that extractor available? Is that open source?
It's in a pull request sitting on the repository at the moment.
Last I checked, there was no extractor for Haskell. It's sad.
I've just rewritten it, so that there's a new one that I'm working on. I'm waiting for my team at Meta to merge my pull request. Is there any more? Yeah.
Can you search by language extension?
Search, as in search modules by language extension? Oh yeah, that would be easy, for sure. Yeah. Yeah.
That's exactly why I wanted to use it last time I looked at it.
Right.
Does that also find
if the information is in the HIE file, that should be easy. It should find Cabal. Yeah. I think there was one at the back, was there?
So isn't building all package the hardest part? Yes. Like how do you get a build plan for all packages?
Oh, I fiddled around with it.
Yeah. Some packages don't even build.
Yeah. Okay. So I it's stackage first of all, and then it's.
On the slide I thought it said package.
Yeah. Well, it's best effort. Yeah. Okay. Sorry. It's stackage. Yes. And also I had to do a lot of deleting of things and tweaking of project files to make it all build. Yeah.
So this is very ad hoc, but we recently did. So as I said, we are looking on how to verify things inside the Haskell ecosystem. So we looked a little bit on what already is there in existing tooling and how well it works, especially with Clash, meaning also supporting index data types. So just as a quick running example, what we used, and I won't have time to show them in code, but I have them for all the examples if you like to see them. So this is a Cray encoder. So all of you should know the standard binary encoding. There's also the so-called alternative Cray encoding, which has the property that with every increment or decrement, only 1 bit flips. And this is quite useful for hardware. This is actually quite easy to implement with certain XORs. And the property we're just looking here is that we can convert to Cray and back, and then we should have basically the identity function. And the idea is really to prove this fact in this case. And I mean, if you look at that and you look at the standard Haskell higher order functions, then this is basically a really easy task to do. I don't only have it in code, but I think you can create this circuitry out of those operations quite easily. So we looked at different approaches. The first one is the basically classical one, where you have your definition in Haskell and you have it in a so-called formal framework, which is a proof assistant in our case, which is similar to a paper for actor we looked at. And then you develop your proof basically on the actor definitions in parallel to the Haskell ones. And this works. This is the classical approach, but we found out that this is quite error-prone because usually you have different people working on these things and then they need to communicate, and you don't have really won a lot by having the proof externalized, because once they diverge again, this doesn't work any well anymore. So we ruled out that. Then we looked at the second approach, that you basically come from the proof assistant. So this is, for example, easy with Acta to generate Haskell code out of it. This gives you a better interface in that regard, or like a well-defined one, but it requires a lot of effort on the tooling, and it requires a lot of people knowing how to do that in the proof assistant, which is also not that easy. And we also stumbled here across the issue that Acta 3HS does not support index data types at all. It just throws an error. So yeah, you need to maintain that, you need to set that up. So this was not very convenient. Then you can also do the other way around. There's the transpiler approach. You basically translate the Haskell back into the proof assistant and do the proof there. The prominent example for that is Haskell to Coq. This also works. We have it working. However, Haskell to Coq is not maintained anymore. It's on 8.8, I think, currently. So this really created some issues. And it's a transpiler, so you have to write a file with rewritings, and then you can basically rewrite your end definition with all definition, and it won't be checked, so you now have no evidence that there's an issue in there. So also, it's better than the classical one because you have a little bit of tooling in it, but it's not really tightly integrated. And the last approach we looked into was basically liquid Haskell. They also have like the proof combinators package these days where you can do equational proofs, and this was sufficient to actually prove this completely in Haskell. And liquid Haskell uses the Haskell semantics of the definitions directly for that. And yeah, so we will continue in that direction. As I said, it's ongoing work, but this was a first experience we made for exploring this a little bit. Thanks.
Thank you. We have time for one or two questions.
Yeah.
So I think the idea of Acta 2HS was that you deliberately write very Haskell-like code in Acta, and you can't do any fancy Acta stuff, and you have to kind of write your proofs externally on the side, which maybe isn't how you'd like to do it, at least you can do it. So
I mean, our goal is to start basically in the Clash ecosystem, so that you have the things defined you need to create hardware in the end.
I was just wondering why the index data types were such a...
No, this was the Acta 2 Haskell. Yeah.
We need index data types.
Yeah, so, yeah. So whenever you get to hardware, you don't have a 32-bit int, but you also may have a 17-bit int and so forth.
So index data types in Haskell?
Yeah, in Haskell. Okay. It's actually not that trivial to actually go from a proof assistant natural type index to a Haskell type index. So there's a good reason this is not supported.
More questions? Right. Thank you. Thank you very much.